Hello class, this is a video tutorial on sketching polynomials. So for any polynomial, the constant term is the y-intercept. The number of roots that a polynomial has is always going to be less than or equal to the degree of the polynomial n. So for example, if you have a polynomial of x cubed plus everything else, since it is x cubed, it is impossible for the graph of this polynomial to have more than 3 x-intercepts. So we're going to call the degree of this n. The number of turning points a polynomial has is always going to be less than or equal to 1 less the degree. So if it is x cubed, the number of turning points that this has must be at most 2. So a degree 3 can only have 2 turning points at most. It could have 0 turning points, but yeah, you get the idea. And lastly, between 2 real roots of any polynomial must exist a turning point. Now, these four properties will help us sketch. Right? Sketch, not graph, because we're only going to be doing rough sketches of these graphs of polynomials of any degree. But first, we should understand the shape of a quadratic and a cubic in general. So, a quadratic is degree 2, and we know it has 2 factors, or 2 roots. When we expand it, it'll look something like this. And the x-intercepts will relate exactly to the roots of the factored form of the quadratic. The value of c is always going to be the multiplication of the roots. So this value of c is going to be alpha times beta. And also take a look. It has degree 2, it has 2 roots at most, and it has 1 turning point. Now just letting you know, it's possible for this to have 0 roots. Let's take a look. If I shift it up like this, it will have no roots. It has no x-intercepts. But in that case, it still fulfills the idea that the number of roots must be less than or equal to the degree of the polynomial. Oh, and lastly, take a look at its shape. It starts here, curves down, and goes back up. And because it has a real root there, well, between these 2 roots must be a turning point. So it starts here, ends here. For a cubic of degree 3, you'll find that these roots, or these factored forms, match exactly to where the graph intercepts the x-axis, and the value of the y-intercept is going to be the multiplication of these roots. And once again, take a look. It has degree 3. It has at most 3 roots and 2 turning points. Now, it's possible for this to have 1 turning point. No turning points, like this. That's still a cubic. But if it has 1 turning point, it's possible for it to have another turning point without a root. See? And lastly, notice how it starts here and ends there. So it starts here, ends there. These are still quadratics and a cubic. This time, though, it has a lead coefficient of a negative. For this, it's exactly the same thing, but now it is concave down. But once again, starts here, ends here. Starts here, ends here. In the exact same way for the cubic, it starts here, ends there. And the same features still apply. Whoops. Now, we're going to extend this to higher degree polynomials, and you'll find that a similar pattern can be found in even and odd degree polynomials. For even degree polynomials, where it leaves, it's starting on the same side. So if it starts here, it'll end on the same side. For odd degree polynomials, it'll start here and end on the opposite side. So even degrees start here, end here if they have a lead coefficient that's negative. For cubic, starts here, ends there if they have a negative. It's flipped if they have a positive lead coefficient. And then from this, we can keep extending it to quartics, which has a degree 4. And notice now, it has the 5. It's opposite to the sign. 3, 1, 4. And since it's degree 4 with a positive lead coefficient, it starts here, does its thing in the middle, and ends on the same side. For degree 5, exact same thing. These roots correspond to the x-intercepts. This is a root of 0. And since it is odd degree, it starts here, ends there. So it starts here, does its thing in between, and ends on the opposite side. For degree 6, I think you get the idea. Lead coefficient is negative. Since it's even, starts here, does its thing, and ends on the same side. Odd degree, starts here, does its thing in the middle, and ends on the opposite side. And you can check for yourself. If you multiply all of the roots, times it by -1, you should get a y-intercept of 1680. Likewise with this, if you multiply all the roots with a negative coefficient, so times it by -1, you would get that y-intercept. So that's the general idea for graphing polynomials. But just to keep this video a little bit shorter, I'm going to cut this off for now. I'm going to leave this for the next video where we do these examples. So I'll see you then. Best of luck.